All right, today we're going to talk about solutions and many different things about solutions we're going to talk about today. So we're going to talk about what a solution is, how things dissolve, what electrolytes are, factors that affect the rate at which something dissolves, factors that affect how much you can actually dissolve, and what a saturated, supersaturated, or unsaturated solution actually is. And so the first thing is, what is a solution? It's just a mixture of things put together. A homogeneous mixture means they're evenly mixed. You can only see one phase, in other words, one part to that. And there are many types of solutions you could have. It could be a solid and a liquid like salt and water. Could be a gas and liquid like a carbonated beverage, or it could be one liquid dissolved in another liquid. So there are all those different types of solutions. But when you talk about the process at which something dissolves, that's called solvation. And what's happening when something dissolves, or how something dissolves in water depends on what the substance actually is. So if you have something ionic like table salt and water, that's ionic. A metal and a non-metal makes it ionic. So when it dissolves in water, what happens is water will be attracted to it because water is a polar molecule. It's got a positive and a negative side. So the hydrogens will pull apart the chlorines, and then the oxygens, when another water molecule comes along, and the oxygen, they share electrons, but the electrons hang out closer to the oxygen, so it pulls apart the sodiums. And so when you have those ions that are free to move around in water, we say that they're electrolytes. And so that whole process there is called dissociation, when water's pulling apart ionic compounds in water. And but water can also just, if a molecule is polar but it's held together by covalent bonds, like something that is a molecular compound, like sugar, for instance, is C6H12O6. And that molecule, if we showed you the structure of it, it is polar, but again, it's got all these covalent bonds in it, and water molecules will surround it. They will surround it and pull it apart into ions, they will surround it, and each individual molecule will be separate, but it doesn't pull apart the individual ions in it, because actually those bonds, they're sharing electrons, and there are no ions in that. And again, so that's called molecular solvation. That's what, again, covalent compounds do. And again, that's called dissociation. That's what happens to ionic compounds when you put them in water. And so here's the thing about ionic compounds when you put them in water. Water separates them into their ions, and they allow water to conduct electricity. And we say that those are electrolytes. And those are the same electrolytes, when they say, if you're exercising or whatever, it's hot and you're sweating a lot, you need to replace your electrolytes, because there are many different ions that we have in our blood that if we start to lose them because we're sweating too much, then you can actually die from that. What happens? I was went to a lot of tennis tournaments with my son when he was growing up, and if it's really hot in the summer and they're playing, sometimes people, if they don't hydrate before these matches, their whole body will start to cramp on them. And it's because they're losing sodium and potassium, those things that are important for muscle function. So again, here's a list of electrolytes that you need. Notice these are just ions that we need in our blood. So we say they're electrolytes when they're floating around in water. And you drink Gatorade because you want the electrolytes that are in Gatorade. It's got sodium, calcium, and stuff like that in them. And so what's actually happening there when you put them in water is, for instance, if you put a battery, with two electrodes in water. So here's our battery here. It would have a negative and a positive side, and usually those batteries have chemical reactions going on that are producing electrons, and those that are accepting electrons. So what will happen is then, so if you put it in water, water itself is not actually a great conductor of electricity. It self-ionizes a little, but it's not the greatest conductor in the world. But it's water with ions in it that allow it to conduct. Because what will happen is sodium ions, if you put salt in water, these ions will start to be separated and surrounded by water molecules. And what will happen is the positive ions will go over here and they will pick up electrons from this electrode. So you got current moving there. The negative ions will go over here to the positive electrode and give up electrons. And so what that then means is you actually have this flow of electrons through water. And so if you have electrolytes in water, that it will conduct electricity because the ions are picking up electrons on one electrode, giving them up on the other, and that allows current to flow through that. I will try to show you that here in a second here. So what I have here is distilled water, and we're looking at the conductivity of that. So we look at the conductivity of distilled water, and here's our conductivity tester. I'm trying to move that back a little bit so we can see it better. All right, so here's our conductivity tester in water, and so it's distilled water, and you can see that it's just a 1, because water, again, there are a few ions in water, so it conducts a little bit, but not a lot. And then this is sugar water, so this is C6H12O6 dissolved in water, but remember that's a molecular covalent compound. Water surrounds it, so it does dissolve in water, but it doesn't pull it apart into ions. So we say that that's a non-electrolyte. It doesn't help it to conduct electricity. A little better than the other one, maybe because of what was on the edge of the beakers when I put stuff in them. And then this is water from the sink. Now think about this. Does this have electrolytes in it? Does it have ions in it? And so our water we get around here is a lot of times ends up on Lake Travis. It's surrounded by limestone. And limestone is ionic. It's calcium carbonate. So water dissolves those ions in it. So it should have a few ions in it. And so regular water from the sink should conduct electricity a bit. And you can see there that it's a 4 because it's got ions in it. So it has electrolytes in it. It allows it to conduct. And then the last thing here is salt water. So there's some salt water. And again, salt, NaCl, are those electrolytes? They are. Water pulls them apart into ions, and then they allow something to conduct. And there you go. You can see that, again, that's a 4 as well, because it's got a few more ions. If I stirred it up probably better, it might be even better than the water that's coming out of the sink. So electrolytes are things, you put them in water, they're ions that conduct electricity. And again, strong electrolytes are things that completely break apart when you put them in water. Weak electrolytes, some things will break apart, just a fraction of the molecules will break apart. And then non-electrolytes like sugar, as an example there. So again, salt would be a strong electrolyte, sugar would be a weak electrolyte. And again, I've listed all the things that you need for your muscles to function properly there. And so if you look at these things and you go electrolyte or not, what you're looking for is, would water pull it apart into ions? So what we're really looking at is it ionic? Because if it is ionic, then it is an electrolyte. So is that ionic? Yes. That means it would conduct electricity when you put it in water. Is this one ionic? No. This one, again, we're looking at 2 nonmetals. 2 nonmetals. They're not electrolytes. Ionic compounds are, again, a metal and a nonmetal. That's what makes an ionic compound. Is this ionic compound? Would this be electrolyte? Yes, it is. It's a metal and a polyatomic ion. And in this case, hydrogen is acting like a metal. So yes, hydrogen's in column 1, and so it would be an electrolyte as well. All right. Now next thing we're going to look at is what will affect the rate at which something dissolves. And what you need to have for something dissolved in water, if you put sugar in water or sugar cube in water, what has to happen is the water molecules have to hit it and pull it apart. So you have to think about, when you talk about factors that could increase the rate something dissolves, you need to know what would increase more collisions, or what would cause more collisions to happen. And so if you increase the temperature, molecules start moving faster, there'll be more collisions. If you stir it up, the molecules are more likely to hit each other and therefore dissolve faster. And if you decrease particle size, so if you had a sugar cube and you chopped it up into small pieces, you would have then more surface area on it, and more water molecules would be able to hit it since you have more surface area, and it would dissolve faster. We can also look at, the solubility of the substance is not all substances, whether or not a substance will dissolve another substance depends on the nature of that substance. So I'll talk more about that in a second, but when we talk about how much you can dissolve in another substance, we say, the solution is saturated or unsaturated. So what does that mean? If you take these water molecules here, there's just a certain amount of space in those water molecules. And so if you start adding salt to it and all the space between the water molecules gets filled up, we would say that that's a saturated solution. After that, if you added more salt, it would just go sit on the bottom. If it was an unsaturated solution, you added more salt, it would dissolve as well because there'd be more space between the water molecules. So there's just a limited amount of space there. And a supersaturated solution, and hopefully at the end of this, I'm going to pause it for a second, I can come back and show you maybe if this is going to work for me. I'm working on something right now. I can show you a supersaturated solution, and that is a solution actually that's holding more solute than it should be able to dissolve. And again, so what do I mean by that? First of all, water, again, whatever the dissolving medium is, like what's doing dissolve, we call it the solvent. And so the thing that you're adding to it's called the solute. So if we start adding salt to water and we fill up all the space between water molecules, we'd say it's saturated. But if you heat water up, it will actually, you'll create more space between the water molecules and it can actually dissolve more solid. Then if you cool it down, it can't hold as much solid, but if you don't disturb it, that solid will stay dissolved, and that's called a supersaturated solution. So the only way you can make a supersaturated solution is to heat something up and then to cool it down. All right, so that. We'll talk more about that, like I said, hopefully at the end. And then some factors that affect this solubility of a substance, like what will dissolve what? Well, we say that like substances will dissolve like substances. What do I mean by that? Well, again, I'm going to try to show you this here. You can see that a little bit there. There you go. All right. Okay, we've got two liquids there. You see them better there. And notice they are not mixing together, because what do I mean by like substances dissolve like substances? Ionic substances, or polar substances, we should say, things that have a positive and negative side to their molecules, will dissolve other things that are polar because they have a means of interacting with each other. So we say like substances dissolve like substances, polar substances dissolve polar substances, but if something is non-polar, it will not dissolve in a polar substance. This is ethyl alcohol at the bottom with some food coloring in it. It is polar. This stuff at the top here is actually paint thinner, and it is nonpolar. And so they have no means of sticking together. I can mix it up. I can mix it up a little bit. It looks like they're going to mix up together, and then they will separate out very, very quickly. And again, because they got no means of sticking together there. So that's what I mean by that. Here's another example of this. Hopefully I can show you this one real quick. Again, this is difficult to move this thing around here to get exactly where I want it to. Anyways, so here's some water again. This is just sand that's coated in plastic, and it's non-polar. Water's polar. You know, it's got a positive and negative side to water molecule. So this sand coating in plastic, it will not dissolve in water. Hopefully you can see that. And there you go. It's not attracted to water at all, so they got no means of sticking together. And you know, I can try to separate them out. Try to do that. Let's see here. Okay. There we go. And the sand is still dry. And again, because it's got no means of sticking together, so that's what we mean. The sand is nonpolar. It's not attracted to water molecules. And again, the water's polar, so again, they got no means of sticking together. All right, so that's what we mean like, dissolve like. Hopefully get back going here with wrap this stuff up. And we say that liquids are miscible if they, again, mix together. If one liquid's polar, the other one's polar, they will mix together. They're immiscible if they don't. And I get a good example of that is oil and water. You know, oil will not mix with water. Oil is nonpolar, water's polar. Lava lamps, that's just two liquids that are, one's polar, the other's nonpolar. That's why they don't mix together. And again, if you look at something like, we have an example of ethanol here. That's the ethanol molecule. There's a polar bond right there. It's a hydrogen bond there. And that's why, again, it's attracted to water. And that's why ethanol would dissolve in water. This is, again, sugar molecule. It doesn't really have hydrogen bonds that water molecule can really, or it does. It's kind of a couple of hydrogen bonds. It's polar, but for the most part, water can't pull that apart. It can just surround it. So that would be a non-electrolyte in water. Again, an example of oil and water, and that don't mix. All right, factors that affect how much you can dissolve. So first of all, temperature will affect the solubility of solids and gases in water, but it has the opposite effect. And pressure only affects the solubility of gas in water. So let's look further at that. So the effects of pressure on solubility, and now we're talking about gases here first. And so here's the thing. You can force a gas into a liquid. That's how bottling companies get carbonation into liquid. So when you buy soda, they bottle them at like 5-10 atmospheres of pressure, and so they force the gas into the liquid. But as soon as you open it up, you hear the fizz there, the pressure is being released, and then the solubility of the gas starts to decrease. And so there's a relationship. There's a direct relationship between the pressure applied to the liquid and the solubility of the gas, and that's called Henry's law. And so when pressure goes up, solubility of gas goes up. So they're directly proportional to each other. You can do problems associated with that. It says, again, solubility of carbon dioxide in water is 0.44 grams per milliliter at 1 atmosphere of pressure. Again, what would be the solubility at 5 atmospheres of pressure, which would be what they would normally bottle liquids at. What you do is take the solubility of the gas, 4 grams per milliliter at 1 atmosphere of pressure. And we want to know what the new solubility is at 5 atmospheres of pressure. And so that would be 0.44 times 5. We'll get our answer there. And we'd end up with, again, 2.2 grams per milliliter. And if you're a diver, you might know a little more about this than other people, because if you're a diver, they teach you that if you go down in the water, there's a certain I don't dive myself, but there's a certain limit to how far you can dive in the water where the pressure builds up enough that it dissolves more nitrogen in your blood. And if you then come up to the surface too fast, you're lowering the pressure too fast, and it'll make nitrogen bubbles in your blood, and it'll give you what's called a binge. It's very, very painful. It'll actually kill you. And if that happens to you, if you come back to the surface too fast, and these gas bubbles form, they'll have to put you in a pressure chamber to try to fix that. But it's very, very painful. Like I said, it could kill you. And here's another practice problem associated with that. So the solubility of nitrogen in blood is 11.5 milliliters per liter at normal atmospheric pressure. What would that solubility be at 5 atmospheres of pressure, which is 50 meters under the surface of the water? So say 11.5 milliliters per liter there at 1 atmosphere. And again, we want to know how much would dissolve at 5 atmospheres, which would be 50 meters under the water. And so you can see that a lot more dissolves there. 11.5 times 5, 57.5 milliliters per liter. And again, so quite a bit more would dissolve at depth. So that's something to consider when you're diving one day, or if you decide to do that. Again, we're looking at the effect now of temperature on gas solubility. And what we're going to have to do is, first of all, understand that when you dissolve something in water and you increase the temperature, things become more disordered. And so if you dissolve a gas in water and you start heating it up, it becomes more disorderly, and gas bubbles will form, and it'll actually leave the liquid. So you can see that as you increase temperature, the solubility of a gas actually decreases, because the gas bubbles will actually leave it. You're forcing the gas into the liquid. The exact opposite happens when you dissolve a solid in a liquid, though. The amount of solid will increase because it becomes more disorderly. And so as you heat it up, the solid particles will start to break apart and then dissolve in water. And so just make sure you understand, we talk about or the solubility of something in water. If we're talking about the solubility of a gas, it decreases when the temperature goes up. The solubility of a solid there, you can see, increases from that. We're not going to work the problems here because we can't see this well enough, and it's not something we're going to hold you accountable for, so don't worry about that. And that's where we're going to stop today. I'm going to try to pause this for a second and show you a demo possible.